All right, so our next speaker is Miguel Angel Cabrera from Universidad de los Andes in Bogota, and he's going to talk to us about granular column collapse, recent advances. Miguel, thank you so much for accepting our invitation. It is a pleasure to have you here. Please start your talk.
Thank you, Yuri. And first of all, thank you for the invitation. It's amazing to be in this session with such an interesting lectures in the group. First of all, I want to say that this work is being work in collaboration with some students, as Andrea Jara, Gustavo Pinzón, or Oscar Polania, some colleagues at the University of Los Andes, like Nicolás Estrada, and some colleagues in Canada. I will show you some experiments we have done at the end. This work probably fits very well with the session, and I'm so sorry if you get tired of seeing so many granular column collapses, but it's such a simple setup, but yet can provide so rich information on the granular flows that I've been amazed with it in the last 5 years. So my talk will be divided in two main topics. I'm going to talk about landslides and what is the importance of knowing how far they go. And I'm going to show you some of the works we have performed this configuration. So first of all, with how far does a landslide goes? Let's think about landslides and infrastructure. So I'm from civil engineering. And in civil engineering, the simplest case for a slope stability analysis is that of this translational landslide. In this landslide, what you have is a wedge of soil that has a triangular cross-section that slides by self-weight. If we assume there is no water, just the self-weight. And this self-weight, for some reason, exceeds the shear resistance of the material. As a result of that, we get a landslide, and that is very canonical in slope stability, and we use it to predict whether or not a slope will fail. However, understanding whether or not the slope will fail is not enough. Here, I show you a very dramatic example of it. For example, here you see a massive landslide that probably engineers were aware that it could fail, but what they were not able to predict was whether or not it will interact with the infrastructure. In this case, it is obvious that this highway in Taiwan was completely blocked. It is a sequence of bridges. Therefore, the reconstruction or the opening of the highway is not an easy task. And knowing how far a landslide will go is of most importance. Another example of this, of calling attention, of understanding the mobility of landslides, is this of an open mine in a highway that connects Bogota with Medellin in Colombia. It's a very important highway where many goods are transported. And what you see is that one of a landslide started occurring here on the top. And knowing that a landslide will occur is not enough, because there was 3 or 4 chances for the landslide to stop. It could have stopped in the highway that connects the mine site with the collection place. It could have stopped a bit below that. It could have stopped at the entrance from the highway to the mine site, but it didn't happen in that way. It didn't stop right at this building where it damaged part of its facade and it blocks the highway. Blocking this highway is very, very crucial because it stops the transport of goods, it has an economical impact, and then it makes the whole issue much, much more dramatic. So here again, understanding how far does a landslide goes is of most importance. And a final example for it is this tragic event in Mocoa, in the southern Andes of Colombia, where about 400 landslides occur simultaneously. These about 400 landslides occur along a geological plane that helped to identify that there was some geological aspects behind the occurrence of these landslides. And what you see in this plot is the darker the color, more landslides occurred within that hectare. So what you see is that many landslides happened right above this, this line with the triangles. But also you can see that there are some rivers and creeks next to that. So how far a landslide gets even more dramatically complicated when you try to mix it with the flow paths. And what you got as a result of this situation is that even though most of these landslides didn't happen near the metropolitan area of Mocoa, the mixture of these landslides with water resulted in the occurrence of several debris flow, mud flows, and other sediment transport processes that damaged a whole neighborhood here on the northern side and killed many people. About 300 people died on the 7th. And a picture of what this debris flow looks like here on the northern side of the San Miguel neighborhood, you can see it here, where blocks of nearly 10 meters side, maximum 10 meter sides, flowed from this top area along a creek, so not a river, just a creek, and ended up being deposited and damaging houses, people, and generating a calamity in this community. So usually as engineers or in general, what we have to understand the mobility of landslide is very not practical tools like limit equilibrium and finite element methods. And these tools are not able to predict this mobility just because they are focused on understanding whether or not a landslide will occur. So it comes to mind this refrain that says, get the right tool for the job. So far, the previous talks have highlighted these recent advances in numerical methods that will allow to understand this mobility. And despite their simplicity, these methods are very promising in simplifying enough the physics behind a landslide and helping us in understand what the mobility of a landslide will be. It is important to understand that a main characteristic between these methods is that they allow to understand what will happen under large deformations, whether or not they are implied or not. These large deformations are necessary for understanding the mobility of mass flows. So given this variety of numerical methods, we have to think what experimental validations we have to understand whether or not the methods are accurate enough or not. So in order to understand that, we need to acknowledge for the complex rheology of granular materials. This complex rheology gets affected also by the grain size, the grain shape, or even these natural nonlinear behaviors. There is also rate-dependent particle-particle and particle-fluid interactions that are of most interest. And there is these micro to macro relationships. We have seen in the previous talks some approaches to that, how to understand how particle interactions reflect on the overall mass flow mobility. And finally, there is some volume-dependent behavior. It's not the same, the mobility of a small volume in comparison with a bigger volume when we have it relative to a general behavior. So scaling all these characteristics is relatively complicated, and that's why we need some simpler methods. One of these simpler methods is the granular column collapse. As you have seen, so I will not go much into the details of why this is relevant, but let's first say just what controls the mobility of mass movement and call back this very wise sentence that says all models are wrong, but some are useful. So we need to remember that even though this is a granular column collapse and we like to think of it as a granular flow, it is not a landslide. It is not what happened in nature, but is simple enough that allows to understand what happens and then extract the fundamentals of those interactions and move it to these natural behaviors. So again, what we have in nature is a mountain with a given slope with many complications in it. We have animals, we have people living next to it, we have vegetation, we have the weather effect. But even though all these things happen, we have a sliding plane. This sliding plane can then be simplified as a block, as a prismatic block. And this prismatic block will show a sliding plane as well. This sliding plane will be there whether or not we change the dimension of this prismatic block. And this is what we call a column collapse. So in a column collapse, we want to abstract all the complexities of a mountain into a prismatic block. Some advances or some examples of this prismatic block has been shown since 2008, 2004. And here I'm just showing you some very nice examples, just because the movies are amazing. These people have done very interesting works. On the top side, you see the column collapse of the fine grains over a layer of larger grains. And you see the very complex dynamics that occur in there. And you can tell that these complex dynamics look very similar to what we see in a monodispersed system, all particles of the same size, here of metallic bits that are released by a magnet. So it's a beautiful example of how to avoid these complex triggering mechanisms. And again, the mobility of the setup looks very similar. What we observe in these configurations basically is to compare how far did the column collapse moved relative to its initial dimensions. These initial dimensions are called an aspect ratio. And as shown by Laurent or Gouchon, this aspect ratio controls the mobility of the flow. And in this mobility, we differentiate between two kinds of column collapses, short collapses and tall collapses. Short collapses follow a power law, and tall collapses follow a different power law. And here in these snapshots, you can tell another additional differences that is not necessarily related with mobility, but it's another feature that appears when we observe the deposits of these column collapses. In a short collapses, you observe a trapezoid deposit, and in tall collapses, you observe more as a pyramid deposit. So one of the aspects I started working on when studying this configuration was what is the effect of the grain size? Because I wanted to develop experiments that were representative whether or not the experiment is big enough or not. So we started exploring the grain size effect by making discrete element simulations of columns where we change the size of the grains relative to the width of the column. So the smallest configuration we could get is this, where you can count about 10 grain diameters in a width of column. And we started increasing the number of grains we use in these simulations up to 150 grains, the width of this column. And again, the purpose of these simulations is to answer the questions at which point the size of the number of grains I add to my system, it does not change the response of the system, does not change the relevant mobility. Here, I showed you some aspects of these collapse stages that Laurent mentioned, where we start with a free fall stage. And this free fall stage that is shown here in this second snapshots is followed by a lateral spreading that occurs relatively at a steady state, and then ends up resulting in a deposit when everything is static. So answering the question of what is the effect of the grain size in the column collapse, we found out that for short collapses, here shown in blue, you need about 75 times the grain diameter to stop having grain size effects. Another way of showing these grain size effects or reading this picture is just say that if I have a small system, the mobility of the system is relatively smaller when I increase a bit the number of particles in the system. I stop having that grain size effect just about 75 times this grain size. And for taller columns, we can reduce this, the strictness of this condition. And we can say that tall columns will avoid grain size effects if they are at least 50 times the grain size of the whole monodisperse systems. So again, here showing the difference between short and tall columns, you can see that by increasing the number of grains in the columns, we start approaching and converging towards a common trend. Then after this was all done for a monodisperse system, we started asking what would happen if we include different sizes in these configurations. So a way to talk about these systems of different grain sizes is to recall the term of fractal dimension. And this fractal dimension is just a way to say that if I increase a parameter d, that is the fractal dimension of a grain size distribution, I start having more smaller particles compared to the largest particles. Here in the left-hand side, you see the grain size distributions of these systems. And what we were testing here is for each grain size distribution that is found to be common to many natural mass flows. So this D1 is a very well-graded curve, and this D35, D equal to 3.5 is very common to rock falls. We were testing whether or not, at which point we start having a very non-grain size effects on the response of the mobility. Just showing you some examples of it, you can tell that the mobility of the system, again, tell by how far does the deposit reach sideways, is very much controlled by the grain size effects if you have a smaller number of particles, When you have a smaller number of particles, the effect that a big particle has on the mobility of the column is very dramatic. And this effect is then attenuated when you start increasing the number of particles involved in the system. And we found that for this case, you stop having these grain size effects of about 50 times the mean grain size of the whole granular system. And this contradicts a hypothesis that was done before, arguing that as you increase the grain size distribution, you're increasing the mobility of the system because of some lubrication effects. We found out that that is not the case, and that was just an issue related to the grain size distribution of the system. The authors of that work started to increase the grain size distribution, but remained constant the whole volume of the column, without noticing that for some cases, the volume of the system was just too small, so bigger particles will have a strong influence on the whole mobility of the system. So we corroborated that you need to have a large enough system, and this was then confirmed by testing one of these very large systems in a simple shear cell and comparing the effective friction we observed and the overall packing of the system, and confirming that under steady state conditions, this static friction does not change as a function of the grain size distribution. So in conclusions of this work, the lubrication mechanism does not explain the large mobility of natural granular flows, such as debris flows and rock avalanches, and the mobility and shear strength of granular flows is independent of the power law exponent of its grain size distribution. So now I'm going to talk to you about a particular setup we developed here in Bogota, and that is inspired by some earlier works of Laurent in 2008. In this configuration, instead of lifting up a gate, we remove a gate that is normal to the plane where the column will collapse. This configuration is very thin in a way that you can see the shadow of each single particle where that is included in this column. Here I'm showing you a video of this, and I want to call your attention to how easily we can see the motion of each particle and have an idea of which particles are moving and which particles are not. So this configuration is very useful to abstract many information. For example, we can abstract the flow fields at each collapse stage, we can tell which parts are moving faster. For example, here at the initiation, we can tell, sorry, we can tell this accelerating phase, how it propagates within the granular column, and how we always observe a very thin layer of grains that are moving faster in comparison to the others. Here in this configuration, we confirm again that we can differentiate between short and tall columns with some small deviations here at the transition point, but with well enough setup that allows to see this richness of behaviors. And just being aware of what happened a few days ago in Tonga, we had this submarine volcano that started to grow and made an eruption on the 15th of January in 2022. The eruption of this volcano caused several issues. It has caused deaths. It had caused a huge damage on all the communities nearby this volcano. And one of these damages was the damage of undersea cable. The damage of this undersea cable is being caused. Here you see the islands of Fiji and Tonga, and here you see a line of mountains. Part of this line of mountains was the Unga Tonga volcano. And related to the eruption of this Unga Tonga volcano, the undersea cable was crossed or damaged of about 30 kilometers from Tonga, uncommunicating the whole island. So this is alarming, and it's alarming not just in these areas with volcanoes, but if you are aware of all the undersea cables, it becomes more dramatic when you can read how sharp is the change of level from the continental crust to the underseas. So you have changes of about 2 kilometers in just a couple of hundred of meters, making very steep slopes where submarine landslides can occur. So we started studying submarine landslides in this planar configuration just by adding some liquid and keeping all the setup the same. Here I'm just showing you an example of how these experiments look like, and I want to call your attention to the very dramatic effect that the fluid has on the motion of particles. Here you see that some particles are starting to swirl during the free fall, and I will just go back again to this video. So, sorry. So you can see how the release of these particles, it's a very collective action where you have some densification of particles that are then released and they fall back to the whole flow and move again. And overall, this collapse looks very different from what we have seen in dry conditions. An advantage of this configuration is that we can also see what happens on the fluid. And here you see just the tracers. We added some liquid tracers that allow us to see what the fluid motion is during this column collapse. And what we observe is that while the particles are moving, these particles are pushing the fluid sideways here on the bottom and dragging fluid on the top. So you have a recirculation, a full recirculation, anti-clockwise in this case, of fluid being dragged inside, pushed outwards. That's why you see this lighter area, and drag over it to be involved in the whole flow. With this configuration, we have seen some other aspects. Some of it I have already mentioned are the velocity distributions on the surface on the whole column collapse. So we can tell how fast were the particles moving. But an interesting feature we observed in this configuration was the deformation of the fluid surface. And this deformation of the fluid surface can be related with the formation of some tsunami waves. I will talk about that a bit more later. Another characteristics of these submerged collapses has been pointed out before in this comparison between dense and loose column collapses. Here, just to be clear, we don't differentiate between dense and loose collapses because the configuration does not allow us, but we can tell whether or not a dilative or a contractive behavior is happening. Here, I'm just comparing the total area we tell that it consists of the columns being consisting of grains, and we differentiate between, here on the bottom with markers, that area that is being mobilized compared with the total area of the column. And I want to catch your attention to this inset, where we can tell that at the instant of release, the column dilates a bit and then contracts. And this contraction goes on and on and on until reaching a very state that sometimes is a bit denser than what was initially, or a bit looser than was initially. But these differences between dense and loose are insignificant because, again, the configuration does not allow big changes. But in terms of what is mobilized, we can tell that at the moment you start increasing the aspect ratio of the column, you mobilize more particles, but eventually, despite the aspect ratio of the column, the amount of particles that are being mobilized, normalized by its area, reaches a very common value, irrespective of its initial column aspect ratio. So now moving again with this generation of waves, also in 2018, if I'm not wrong, the Krakatoa volcano had an eruption, and it had this particularity that part of the volcano was immersed and part of the volcano was on air. And what the collapse of this was a partially saturated landslide. This partially saturated landslide was studied in this configuration, generating a tsunamigenic wave. As you can see here, I will move this video back again. You can see how what you see is first a paddle moving the water sideways, but then the competition of particles getting in and a very sharp fluid front that is competing between the percolation of fluid and the particles getting in. These complex behaviors are behind the formation of a landslide, of a tsunamigenic wave, and this tsunamigenic wave can be easily studied in this configuration as a function of the relative depth of submersions of the column. So in this study, we kept the column configuration constant, so the aspect ratio is constant, and we changed the fluid depth. Because of the possibilities with this configuration, we can distinguish between water, saturated particles, and dry particles very easily, and we can tell the velocity profiles within the column collapse. Another characteristic we can monitor is using a very simple space-time configuration. We can tell at which instant the wave reached its peak amplitude and what was its propagation stage. So we followed the wave amplitude, and we started relating with this submergence ratio, how deep was the bottom of the column being submerged. And we came up with these results. So we changed the level of submergence, and we see that for shallower columns, it means that shallower deposits of water, the higher the amplitude of the wave was generated. We compare it with other experimental results, and we see how all of these collapses together. And as a result of it, we propose a very simple analytical answer that is just relating the geometric aspects of the column with its centers of mass of the center of mass of the fluid, the center of mass of the column, and that gives a length, a characteristic length called L. This length is then related with the fluid depth, and just by relating it with the density ratios, we can tell how the wave amplitude can be predicted. And you can see here it's how amazingly the results collapse very well. So now just approaching to the end, I have been working on this configuration with other effects like grain shape effects. And here you see the collapse of a column consisting of elongated particles in air and in fluid. And you can see in fluid how an additional behavior happens. Here you see the fluttering effect of particles that are just settling down, and how the whole collapse sequence is very different from its counterpart in a dry case. Another example I've been working is on these grain size effects, here again with these grain size distributions, but in immersed cases. work that is currently under review. And we have found that water does have an effect on the collapse of a column. And this effect is basically in the failure plane. If you have a monosphere system, your failure plane will be very, it will be cover the whole column collapse at this initial accelerating phase. But if you have a grain size distribution, the failure plane is very sharp and then propagates backwards. Another work we have been done is using these transparent soils and studying the effect of initially loose or initially dense configurations. And what you can see here, when you see these light colors, is just that air is being entering the column. And you see that when the column is loose, air does not enter, but if you have a dense configuration, air starts to enter and weakens faster over the column collapse and generates this very sharp configuration that can be related again with the grain size distribution. So in conclusion, and going a bit ahead of time, we can say the granular column collapse is an equivalent system of larger dimensions, is very useful, and allows a systematic exploration of landslide mobility, and provides an opportunity to study very complex processes with particles, with particle fluid interactions, particle gas interactions, fluid gas interactions in a very controlled way. What's next? I have now anticipated. We're studying larger granular columns to understand which are the effects of these very complex interactions. We are aiming to provide more of these experimental data in order to validate these advanced numerical methods. And we hope that we are able to understand what is the effect of grain size and grain shape in the collapse of these configurations. So with that, I finish. I thank the funding provided by the National Ministry of Science, MinCiencias, and again, thank my collaborators. Thank you again for the invitation and thank you for your attention.
Thank you very much, Miguel. It was an excellent talk. Very nice. We learned a lot of phenomena, different phenomena that you've been studying. It's been very interesting. So we are now, we have many questions. I didn't see who one raised the hand first. So if you don't mind, I will do it alphabetically. Albans, can you start, please? Sorry about that.
Thank you, Yuri. I'll be very quickly. Thank you very much, Miguel. Very interesting. I have two questions. First, yes, which is the role of the cohesion in the granular collapse? If it changed a lot of the results, and maybe you can we have an accident in Minas Gerais where a large rock has toppled over a boat with several victims, unfortunately. And another question is about how the politician support your work in your country, because here in Brazil we have a lot of problems with this issue.
Thank you for the question. So answering the first one on the role of cohesion, let's consider cohesion in a very broad sense. Cohesion as the added shear strength between two grains that is not a result of its friction, but of something else. So if cohesion is understood as that, we do not study cohesion either in these dry cases, because the grains are completely dry and there is nothing in between its contacts. And in the cases where the collapses are submerged, we added something to reduce surface tension. So there is no trapped air between the grains. So there is no cohesion again in this case. But there is an ongoing work that stopped because of COVID. And I want to see if I was lucky enough to add the slide with that. So sorry, I think I haven't added. But one of the things we started studying was we filled up the whole column, and then very slowly we started to decrease the fluid level to reach it again so that the whole system is with air. In that condition, we formed some water bridges between the particles. Therefore, we induce some cohesion in the system, and the collapse changes completely. It changes a lot. And this cohesion, it's very similar to, it generates a collapse that looks very similar with this, generating a very steep failure plane. And this steep failure plane then retreats as the time goes by until reaching a stable configuration that is not a deposit, a trapezoidal deposit, nor a triangular deposit, more like a sharp, steep front and a triangular deposit. That is something that we look much on nature. So that is cool on that side. It's still ongoing work. And I hope that my students manage to get the results soon. And talking about funding with this is not easy because they consider that the setup is too simplified. And the more traditional people that fund these configurations or that fund this study, are more on the philosophy that you need to reproduce the complexity of nature as complex as possible. So they don't like simplicity, and it's challenging. But luckily, I got some funding on that with some ideas that help to convince them that simplicity is good enough. And I hope that I'm successful in some calls that I'm expecting the results now to that. It is not easy in our countries. I understand that. Yeah. But yeah, it is what it is.
Very good, Miguel. Thank you.
Thank you, Aldous.
Laurent, can we have a quick question, Laurent, please?
Yeah, just a quick one. And you are on the right slide for that, actually. So it's perfect.
Good.
So usually people, they relate basically the maximum amplitude of your tsunami wave with respect to a Froude number. In your case, you have done a ratio of the initial state, or how does that relate basically with this Froude estimation usually used? Do you know that, or have you tried?
We haven't computed directly, and I remember I had some similar questions before, and I'm aware that the Froude number here is not exactly the same, or is not within the same range as you will expect in nature. And that is a huge but when you see these overall mechanics. But what I want to call the attention is that if you ignore what is happening in the kinematics of the process, and you allow me to ignore it, and just compare which are the initial conditions, aspect ratio, and fluid level, and which is the result, wave height. If you just see the problem as a picture of those two quantities, you can predict what will be the wave amplitude in relation with the initial conditions. And I find that very advantageous, because if you ignore the kinematics, that is something that usually you don't have when you study the tsunami generated by a volcano or the tsunami generated by a landslide. You usually don't have information of those kinematics, but you do have information of the initial configuration of the volcano or the initial configuration of the landslide. Then you can try to relate both. I know that is not the most physically correct approach, but it's useful.
No. It's not what I meant, because I agree 100% with you. It's basically everything is usually done with the Froude number, which is meaningless. I mean, which is not predictive one, but there's lots of scaling you did that, and I was wondering how you can relate that, and I agree that what you should do is basically to find it from the initial state, but it was just a question on how to relate with previous work on Froude number. But okay, thank you very much.
Thank you.
So real quick, I haven't, but I know that there are two ways to compute it. One way will be with the velocity of the collapse. So either we take a mean velocity at each of these stages and we can plot the evolution of this Froude number, or we can see it in terms of the wave and see the celerity of the wave and use that velocity to compute the Froude number. That will give two different answers, but we haven't done it.
Let's leave this discussion here. We are running out of time. Genchao, if you have a very short question, please ask. And Miguel, could you please answer very quickly? Go ahead, Genchao.
Yeah. Thank you. So my question actually is very short. So recently we are trying to build a new experimental setup for the granular column collapse. So I do want to ask, in your case, it is we call it a planar granular column collapse, which is simplified in 2D. I think the advantage is you can see the particles clearly in the pictures. But I do want to ask, when you simplify the whole problem into 2D, do you expect there are some influence on the dynamics of the particles? Because in 3D, for example, we can have velocity fluctuations in the span-wise direction.
Yeah. The very, very quick answer is no. If you assume that this is a very simplified version of a complex process. If we are saying that everything is simplified, having a simplified of a more simplified is still simplified. Mm-hmm. So here, all these cross-section fluid fluxes and all the side processes are not possible, and we can sleep calm to say that this is enough. And what I want to say is that you see very complex processes as well in more thicker setups, and here we see them. So at the end is the same. It's just how comfortable are you with these simplifications? One of the big problems of this configuration is that you can only use monodisperse systems. So polydispersity is not possible. And that is an issue for me. That's why there are other setups, but that's the advantages of experimenters. You can use your simplifications to your advantage. And this is one I found very useful.
Okay.
Very good. Thank you very much, Miguel. Thank you, Genchao, and all the others for the questions. Let me finish here.